Good morning everyone. Welcome back to the channel, and today our topic is real numbers, which is very important in 10th class CBSE, and you can score how many marks? 4 to 6 marks in this chapter very easily, and I'll make this chapter very simple for you so that you will never forget. Okay, take out your books. We'll start the chapter. First of all, real numbers. What are real numbers? All the numbers we use are combined to real numbers. I'll break down these real numbers into simple parts so that you can easily remember them. See, first one is natural numbers. Natural numbers start with 1, 2, 3, so on up to infinity. Next, whole numbers. If you see the difference between natural numbers and whole numbers, only difference is in the whole numbers we have added 0. In integers, if you see, we have added negative numbers along with 0, 1, 2, 3. Okay, so see, these three I have written in the increasing order. See, natural numbers with 1, whole numbers with 0, and integers with negative numbers. And one more type of number is rational number. Rational number is nothing but which are written in the form of p by q, and p and q should not have any common factor. For example, I'll write here. Okay, if it is 3 by 2, 3 and 2 are not having any common factor except 1. Okay, except 1. See, if you write the factors of 3, only 1 and 3, right? If you write the factors of 2, only 1 and 2, right? So we are not having any common factors for 3 and 2 except 1. If that is in the form of, if two numbers which are not having any common factors and they are in the form of p by q, they are called as rational numbers. Okay, irrational numbers means nothing but they are not in the form of p by q. In the coming chapters, I'll explain very deeply about rational numbers and irrational numbers, how to determine them after division, after getting a quotient. How do we determine whether they are rational or irrational? I'll explain in the coming chapters. Okay, our next topic is Euclid's division lemma. What is it? Euclid's division lemma. Okay. Very simple. Okay. I'll go with definition first. But it is very simple. We already known it. Okay. The definition is, if we are having suppose two positive integers. What are those? Let's say a and a comma b. Okay. Then a is equal to bq plus r. For this, condition is 0 less than or equal to r less than b. And second one is q, we know q is the quotient. And r is the, what is r? R is the remainder. Okay. This is Euclid's division lemma definition. Okay. If we compare this with the rule we know, that is dividend is equal to divisor into quotient plus remainder. Okay. See, nothing but Euclid's division lemma, they have given one statement like a is equal to bq plus r. I am comparing this with this one because we have already know this, right? So that if I explain in this manner, simply you can remember, you will never forget it. Okay. So I'll explain with an example. Okay. Let us take a number a number 26 divided by 5. Okay, whereas 26 is the dividend, 5 is the divisor. Now we'll verify this Euclid's division lemma using this example so that you can understand very easily. 5 divided by 26, right? Now 5 5s are 25. What will be the remainder here? 1. Now we'll write quotient, remainder and divisor. Okay, what is quotient? Quotient is 5 here. This is the quotient, right? And this is the remainder. What is remainder? 1, right? What is this? Dividend. Sorry, divisor. And this is dividend. Now we'll verify whether this equation is satisfied or not. Okay, for that we'll first calculate this one, BQ plus R. The number obtained after this calculation should be equal to A. Okay, A means nothing but dividend. Okay, B is divisor, Q quotient, R remainder. First we'll calculate this part, that is divisor into quotient plus remainder. Okay, what is divisor here? 5. So divisor is equal to 5. Divisor here is B, right? As per the definition. So B is equal to 5. Q is equal to 5. R is equal to 1. Here what should we find here? B, Q plus R, right? So 5 into 5 plus 1, right? 25 plus 1. What is it? 26, right? What is the dividend here? 26. Hence, our Euclid's division lemma is verified. Very simple. 26, which is nothing but dividend. And one more condition is there. Have you observed this one? Remainder should be always lies between 0 and divisor. Okay, we'll see whether it is verified or not. What is the remainder here? 1. What is the divisor here? 5. Is 1 less than 5? Yes. So this condition is also verified. Okay, very important topic, children. Okay, children, our third topic is Euclid's division algorithm. Our topic is Euclid's division. Our third topic is Euclid's division algorithm. Okay. This is to find HCF of two numbers. This is to find HCF, okay, of two numbers using that Euclid's division lemma. Okay, I'll explain with an example. It will be very easy for you to understand. Okay, let's take two numbers. Okay, 135 and 225. Okay, now we'll find HCF of these two numbers using Euclid's division algorithm. The first thing is divide bigger number with smaller number. Okay, 225. How much? 135. Okay, 135 ones are 135. What will be the remainder? 90. Okay, as per Euclid's division lemma, 225 is equal to 135 into quotient, right, plus remainder. What is remainder? 90, right? Again, the second step is, what is the divisor here? Take this one, okay? Now, divide this 135 with 90, okay? 90, 135, 90 ones are 90. What will be the remainder here? 45. Again, using Euclid's division lemma formula, dividend is equal to divisor. What is the divisor here? 90 into quotient. Plus, what is the remainder here? 45. What is the remainder here? 45, right? Again, the next step. I'll tell you how long we should do this, okay? Now, take 90 here. Okay, 90 is equal to 90. We should divide this 90 with which number? The previous remainder, right? So 45, 90, right? 45 into 2, 90. The remainder is 0. So how we should write 90? Divisor into quotient plus remainder. What is divisor? 45 into 2 plus 0. Did we get the remainder 0? Yes. So we should stop this process here. Stop. Okay. Now what is the HCF is? The last divisor is the HCF itself. Right? What is the divisor? 45. Now our answer is this one, nothing but HCF of 135 and 225 is 45. Have you understand this topic? It's very easy, guys. See, I have wrote one arrow here. See, divisor to dividend, divisor to dividend, and remainder will be the next divisor, right? Here also remainder will be the next divisor. How long we should do this process? Until we get the remainder as 0. And what will be the answer? The last divisor will be the answer. Nothing but HCF of the numbers we have taken. Okay? An important tip for you children. See, don't ever write the answer directly. If you know also, if they have given small numbers also, don't write the answer directly, because you will get marks for each and every step. Okay? See, do this. Write this. First take the numbers, first step, and this step. After that you do the division here. After that this one. After that you do the division here. For all these steps you will get the marks. Okay? Don't ever write the answer directly in the board exams. You'll score high marks for each and every step. Okay? Okay children, our next topic is fundamental theorem of arithmetic. Okay? Very easy children, very very easy and very important theorem. Okay, very important theorem. The theorem is the theorem statement. Okay, every composite number can be expressed as product of prime numbers. And this factorization is unique. Okay, I'll explain it with an example. Okay, don't worry children, very very important theorem and very simple. But before that, children, do you know prime numbers? Prime number. What is a prime number? Nothing but okay, what is prime numbers means it is having only which is having only two factors, right? Only how many factors? Two factors. The number itself and 1. Okay, how many factors? Exactly two factors. The number 1 and itself. Example of prime numbers are 2, 3, 5, okay, then 7, 11, 13. Okay, remember this one, only one even prime number is 2. Other prime numbers are odd numbers. We are having only one prime number which is even, that is 2. Okay, now going back to our topic, that is fundamental theorem of arithmetic. Take a number, that is let it be 36. Okay, okay, 36, and we should, in prime factorization method, we should always take the least prime number to divide this number. Okay, clearly observe my process. So least prime number is 2, right? And 2 is a factor of 36, right? How many times? 2, 18 times. And then also 2. How many times? 9. The next prime number is, with 2 this is not divisible, right? So go for 3. 3 ones are 3 threes are. Again 3 ones are, right? 2 18s are 36. 2 9s are 18. 3 threes are 9. 3 ones are 3. Now write all the factors like 2 into 2 into 3 into 3 into 1, right? How many 2's are there? 2 2's. So write it as 2 square into how many 3's are there? 3 square into 1. Okay, this is the method and this is unique. This factorization is our next topic is nothing but application of this prime factorization. What are those applications? Application of prime factorization. What are those? To find HCF and LCM. If you remember, we have found HCF using Euclid's division lemma also. So take two numbers. Okay, let it be 36 and 60. We'll find first HCF. HCF means, what is HCF? Highest common factor. Okay, take 36. See, in the above explanation, I have done prime factorization for 36, right? What we got? 2 square, right, into 3 square into 1. Okay, our next number is 60. Let's do prime factorization for 60, right? Least prime number is 2. So 2 with 30. The least prime number again is 2 with 15. So 15 is not divisible with 2, right? Our next prime number is 3. 3 5s are, again 5 1s are. See, if we write in the form of powers, 2 into 2 into 3 into 5, right? 2 into 2, 2 square into 3 into 5, right? Okay. Now, how to find HCF using this prime factorization technique we'll see, okay? For 36, after doing prime factorization, we got 2 square into 3 square into 1, right? For 60, after doing prime factorization, we got 2 square into 3 into 5. See, we'll see what are the common factors here, okay? 2 square, right? Here also 2 square, 2 square. We are having 3 prime numbers here, 2, 3, 5. In that we have to take common prime numbers factors, okay? See, the definition itself is, the name itself is highest common factor. So we should take the common number, that too highest common number. Okay. So regarding to what is the highest common factor? 2 square, right? In this we are having 2 square. Here also we are having 2 square. So HCF 2 square, right? And the next prime number we are having is 3. Here we are having 3 square, right? It means that 3 into 3 square means 3 into 3. But here how many 3's we are having? Only 1 3. So how many 3's we are having in common for two numbers, that is 36 and 60? Only 1 3, right? Here 2 3's we are having, here only 1 3. So how many 3's we are having in common? Only 1 3, right? The next number, if you see 1, see 1 is the common, no need to write 1. The next number is 5, right? In the 60 we are having 5, but in the 36 we are not having 5. We should take only common factor. We are not having 5 as common in 36 and 60, right? So that's it. This is the HCF, right? 4 into 3, 12. Understood? See, now we'll find LCM, okay? Using this prime factorization method. Okay, LCM. I think all of you know what is LCM. Least common multiple. See, for this you can take simply highest powers, okay? Highest powers. No need to be in common. Directly you can take highest powers. See, we are having how many prime numbers? 2, 3, 5, right? For 2, what is the highest power? In both the terms also the highest power is 2. Here it is 2 square. Here also it is 2 square. So coming to 2, what is the highest power? 2 square, right? Next, coming to 3, what is the highest power? 3 square or 3? 3 square is the highest power. So 3 square, right? The other prime number is, and the last prime number is 5, right? See, in the LCM, we no need to have a common factor in both the numbers. Just we have to take the prime numbers and highest factor of those prime numbers. This is the prime number, right? Highest power is for 5 is only 5 power 1. So directly I am writing 5 power 1. 2 square 4 into 9 into 5. Okay. 36 into 5, right? 180. So LCM of 36 and 60 is 180 and HCF of 36 and 60 is 12. Very simple. See, we have one more important formula. See, in the last example we took two numbers, right? 36 and 60, and HCF of these two numbers is 12, right? And LCM is 180. The formula is regarding these two numbers only, these two HCF, LCM, and regarding this, the formula is HCF into LCM is equal to product of the two numbers, okay? HCF into LCM, right, means 12 into 180. Okay, 12 zeros are 0, 12 eights are 96, 12 ones are 12 plus 9, 2160. Okay, in HCF into LCM is 2160. Now we need to find the product of two numbers also, that is 36 into 60. 0 as usual, 6 6 are 36, 6 3s are 18 plus 3 21. Right, both are same, right? So our formula is verified, right? HCF into LCM is equal to product of two numbers. Very important formula. Okay, so our next topic is irrational number. Okay, irrational numbers. Okay, we know that they are not in the form of P by Q, but instead of this we need to remember this one. You can easily understand whether it is a rational or irrational depending on the statement I am giving now, that is decimal expansion. Expansion is non-terminating and non-repeating. Okay, I'll explain this definition for rational numbers also, how it will be the decimal expansion. Okay, in the next topic, that is our next topic. But now I am explaining only this irrational number decimal expansion. Okay, it is non-terminating and non-repeating. Okay, we'll prove that now. It's a proof that root 2 is an irrational number. Irrational number. Okay, we'll see how to prove this one. Okay, this is the proof, right? What we need to prove is that irrational number. So for that, you assume it as rational number first. Assume root 2 is rational. Rational number means it will be in the form of P by Q, right? Where P and Q are not having any common factor. That is the definition, right? So root 2 is equal to P by Q. Now squaring on both sides. Okay, then root 2 whole square is equal to P square by Q square. Root 2 whole square means square root cancel. 2 is equal to P square by Q square. So 2 is equal to P square by Q square, right? Now what will be the P square here? I'll write again here. 2 is equal to P square by Q square, right? P square is equal to, we'll take this here, okay? 2Q square. See, I think all of you know that if any number is the multiple of 2, then that is an even number. If you see 2, 4, 6, 8, these all are multiples of 2, right? I think all of you know multiples. Okay, 2 1s are 2, 2 2s are 4, 2 3s are 6. Multiples are nothing but the answers we get after writing the 2 table. Okay, multiplying the same number with all the other numbers, then the result we got after this multiplication is called multiples of this number 2. If it is a multiple of 3, write 3 table, answers will be multiples of 3. If you want multiples of 2, write 2 table, these answers will be multiples of 2. And coming to the topic, even number is nothing but multiple of 2. Here P square is 2 into Q square, right? Nothing but P square is multiple of 2. So what is P? P is an even number, right? First thing, we got information regarding P. Now we'll see the information regarding Q. Okay. P is an even number, right? So nothing but P is a multiple of 2, right? Let the P be 2 into K. Now substitute this P value in the above equation. Let it be 1. Okay. Let P is equal to 2K and substitute P is equal to 2K in equation 1. Okay. Here. Now 2K whole square is equal to 2Q square. 2K whole square, right? 2 square into K square. What is 2 square? 4. Here K square is equal to 2Q square. Have you understood this one? I am squaring both 2 and K. Okay. 2 square is 4. K whole square is nothing but K square. So you can cancel this 4 with 2. Okay. Q square is equal to 2K square. See, again this Q is also a multiple of 2. Right? Q square is equal to 2 into K square. Right? Q is also a multiple of 2. Then what is Q? If any number multiple of 2 is an even number. So Q is also an even number. Okay, children. Now, so both P and Q are, what are they? Even numbers. Right. P and Q are even numbers. If P and Q are even numbers, they will have common factors. We'll see. Let the P be 2. Okay. And Q be 4. Let it be P. Let this be Q. What are the factors of 2? 1, 9, 2. What are the factors of 4? 1, 2, 4. 4K. Right? Factors of 4 means see 1 into 4, 4. Next 2 into 2, 4. So 2 is a factor, 4 is a factor and 1 is a factor, right? See, P is having factors 1 and 2. Q is having factors 1, 2 and 4. See, neglect this one. No need to check the one. But we are having 2 here. Here also we are having 2. P is having one factor 2 and Q is also having one factor 2. It means that both P and Q are having a common factor 2. Right? P and Q are having common factor. Is it a rational number, children? Is it a rational number? Tell me. No. Because what is the definition of rational number means? It is written in the form of P by Q. And P and Q should not have any common factor. PQ should not have any common factor. Right? But here we are having this P and Q are having common factor. So we have assumed that initially we have assumed that root 2 is rational. This is our assumption, just our assumption, and root 2 will be in the form of P by Q. What happened in the last? That P and Q are having common factor. So root 2 which we have written in the form of P by Q is not a rational number, right? If it is not a rational number, what is it? A rational number, right? irrational number, right? I can tell you, see, root 3 and pi, these are also irrational numbers, okay? I forgot to tell you in the starting examples of irrational numbers. Okay, root 3, pi, root 2, see, root 2, these all are irrational numbers, okay? See children, I have given the decimal expansion information of irrational numbers, right? Like decimal expansion of irrational number is non-terminating and non-repeating. But I have not told you about the decimal expansion of rational numbers, right? Our last topic is that one. Decimal expansion of rational numbers, okay? For that we have two conditions, two statements, okay? First one is terminating decimal. It can be terminating. If it is non-terminating, it should be repeating, okay? Terminating is okay, it will be ended. If it is not terminating, then it should be a repeating decimal, okay? I'll explain with an example, don't worry. Let us take 1 by 2, okay? 1 by 2, see, if we divide 1 by 2 to 1, 0, okay, to 5 are 10, right? What is our answer? 0.5. See here, I am dividing 1 with 2. But 2 is greater than 1, right? So I have taken 1 0. So for here 0. Okay. 5 to 5 are 10. Answer is 0.5. It is terminating, right? It has stopped here. This is the example for first one, terminating. It is not expanding like 0.532, so on. It is not like this. Okay. It has stopped here. We got the answer at 0.5. So it is terminating decimal. And we'll take example for second one also. That is non-terminating repeating decimal. 1 by 3 if we take. Again 1 is less than 3. Again 0. Put a 0 here. Decimal. 3 3s are 9. Again 1. Again we have decimal, right? So 0. 3 3s are 9. Again 0. 3 3s are 9. See, we are not getting the remainder as 0, right? And our quotient is go on expanding. What is our answer here? 0.333, so on. Right? This is non-terminating. We are not getting remainder 0. So this quotient is go on repeating. Non-terminating. It is not stopping anywhere. And what is the definition of repeating here? Repeating means if you see the numbers 3, 3, 3, the same number is repeating, right? So the rational numbers we are having two definitions. Either it should be terminating decimal. If it is non-terminating, the number should be repeating. Okay, like 0.333, or we can also have like 0.121212 like that, or 0.12125. We can also have like this, not only with single number, 2 digits or 3 digits can also be repeated. See here 1 2 1 2 1 2 is repeated, right? Here 1 2 5 1 2 5 1 2 5, these all are repeated, right? We can have any number in the repeating. One number we can repeat, two numbers or three numbers. We can have any numbers, okay? If it is non-terminating. If it is terminating, directly we'll get the answer. No case of repeating. Okay. See, you can verify this with 1 by 7 also. Okay, an important trick is that here how to find whether it is terminating or non-terminating without division, without using this division means in the denominator we should have either 2 or 5 in the denominator, then it will be a terminating decimal. Okay, you can directly tell the answer without doing this division just by seeing the number in the denominator. See, my first example is 1 by 2, right? What are we having? 2 in the denominator, right? Either we should have only 2 or 5 in the denominator for terminating decimal. Here we are having 2 and the answer is terminating decimal, right? Okay, finally our chapter is done. So now we'll write what are the topics we have discussed. Our first topic is real numbers. How many topics we have covered? Real numbers, Euclid's, division lemma, right? Next, Euclid's division algorithm. Fundamental theorem of arithmetic. And HCF and LCM. Irrational numbers. Decimal expansion. Okay, homework problem for you are 2 problems. Okay, this 1 by 7. Okay, you should find it whether they are terminating or non-terminating. Okay, terminating or non-terminating decimal you have to find. Hint is this is a rational number. Okay, and find the HCF and LCM of 24 and 60. Okay, second question is find HCF and LCM of 24 and 60. Okay, if you understood everything, comment real numbers done. Okay, in the comment section. Okay, in the next video I'll discuss all the important board exam questions asked in this chapter. Okay, in the real numbers chapter. Okay, don't forget to like, share and subscribe. See you in the next class.